So Bayes' law is what we're working on in this lesson. And what Bayes' law does is it helps us learn something from imperfect information. And because most of the information we get is not perfect, it turns out that Bayes' law is very awesome. We use it a lot. So I'm going to develop the idea behind Bayes' law in a pretty conventional way in the context of thinking about screening for a disease. Okay, so we're going to look at this as a probability model where we've got two events that we care about. Okay, so one event, we'll call it D, is the event that the person being tested has the disease is present. And the other event is that the test that we're thinking about here is positive. Test. So just kind of wrapping reins around the model. We're thinking about the other case, D complement. There is no disease, the person is healthy. And the complement of a positive test is a negative test. Okay, so those are the events that we're thinking about. Okay. And what we're going to do with Bayes' law is we're going to take a set of information that we often find ourselves with and use it to figure out a thing that we're often interested in. So Bayes' law is not a complicated thing by any means. The derivation is really simple, and you might even say obvious. What's so useful about it is it just fits a very common situation we can find ourselves in. It's a kind of a common set of information and set of questions that we face. Okay, so let's say that we know the following things, and these would be things we would often know if we were being tested for a disease. Okay, so one thing we know is the probability that the test comes back positive given that the person actually has the disease. Okay, so we might call this the true positive rate. In epidemiology, they call this the sensitivity of the test. That doesn't matter for us. It's a kind of a medical lingo here. And you might be thinking, okay, well, if we know the probability that the test is positive when the person has the disease, if we subtract that from 1, we know the probability that the test is negative when the person has the disease. So let's use a different color for the things that we can infer. So we can infer the probability that the test is negative given that the person has the disease, because this is 1 minus the true positive rate. Minus P conditional on D. Okay, and kind of thinking about that in terms of the phrases that we use in medical testing, this would be false negative, right? Okay, we're in the world where, yeah, the person really does have the disease, but the test is telling us that it's negative here. So we know the probability that the test comes back positive when the truth is that there's disease. From that, we can figure out the probability that it comes back negative when the truth is the disease. So remembering kind of the basic thing about conditional probabilities, when we're conditioning on the same event, that's when probabilities have to sum to 1. All right, so what else would we probably know? The other thing we probably know would be the true negative rate. Okay, so the probability that the test comes back negative when there is no disease, when the person is healthy. Okay, so this is the true negative, right? And yeah, you got it. From that, we can infer the false positive rate. And the probability that we're in the world of no disease, what's the probability that the test says, oh, guess what, you're sick? That is the false positive rate, which would be 1 minus PC conditional on DC. Okay. So these two things, the true positive rate and the true negative rate, these would be things that like clinical trials would establish. That's the sensitivity of the test, and the true negative rate is sometimes called the specificity. All right. One other thing that we're likely to know that we need if we're going to do Bayesian analysis here is the overall probability of having the disease. Okay, before you were tested, how likely was it that you had the disease? So we might call this the baseline incidence, the prior probability of D. All right, so this, all of this in black and purple is stuff that we know or we figured out from things that we know. And what we want, and what Bayes' rule is going to let us calculate, is we want the probability of D conditional on P. Okay, what is this? This is the probability that if you get that positive test result, how likely is it that you are really sick? Okay, all right. So I'm going to go to the next page. We'll kind of keep in mind the set of things we know here. We know the probabilities of P and P complement, conditional on D and D complement. And we also know the probability of D, but what we want now is a probability where we're conditioning on the positive test result happening. So another way people sometimes think about Bayes' law is it's letting us switch what's conditional on what, and that's a perfectly fine way to think about Bayes' law. Okay, so keeping that idea, what do we want? We want the probability of P. No, we don't want, that's one of the things we know. We know that we have the P, right? So we're in this world where we've gotten our test results and it is positive. Okay, so the positive test result is here on that side of the conditioning bar. What we want to know is, well, does that mean for sure I'm sick? Well, no, it doesn't mean that, because we just said that there's a probability of a false positive here. But that's not quite the same thing. The probability of the false positive was when we knew somebody had the disease, how likely was it that the test said positive? And here what we want to know is, like, we know the test really did say positive. What's the probability that I have the disease? And so maybe the most profound idea in talking about Bayes' law is to realize that those numbers are not the same thing. So we want this. So let's think about how we would get that, and let's think about the kind of the definition of conditional probability. That's where we usually start here. So that is the probability of D and P divided by the probability of P. Same definition as in the last set of lessons. If we're looking at the probability that I have the disease conditional on the positive test, well, it's the joint probability divided by the probability of the conditioning event, just like it always is. Okay, and I've got all that information where we are conditioning not on P, but on D, and that can actually help me here with the numerator. Okay, I'm going to switch now to kind of the figuring out part of Bayes' law here. I'll switch to nice pink for that. Okay, so I can rewrite this probability of D and P as the probability of P conditional on D times the probability of D. Just using the definition of conditional probability here, okay? If we had wanted to find this probability, we know it's the same numerator divided by a different denominator. The cool thing is, this is the probability that I have. And it turns out I know this too. So if I have the sensitivity of the test and the baseline incidence in the population, that's what this is. This is the true positive rate and the probability that I have the disease before getting the test, I can figure out this joint probability from using those. That's what I'm going to do. And the other thing I can do, the other thing I want is this probability of getting a positive test, kind of the unconditional probability of getting a positive test. Oh, I know how to calculate those too. That's a law of total probability calculation that I can do. Check this out. The probability of P is, what is it? The probability of P conditional on D is the probability that we're in the world of D, plus the probability of P conditional on D complement times the probability that we are in the world of D complement. Okay. Same law of total probability that we've done in other contexts. Here, what are the ways I can get a positive test result? Well, I can get it as a true positive, or I can get it as a false positive. What's the probability of true positive here? Probability of a false positive weighted by the probability that we're in the world of the where a positive would be a true one, and the world where a positive would be a false one. The probability that I have the disease and the probability that I don't. So let's just kind of keep going with admiring this. What we did in the numerator was we used the definition of conditional probability. And what we did here in the numerator is we used the law of total probability. But the main thing is what we got here, this is Bayes' law. That is exactly it. We want to figure out how to, if we want the probability of D conditional on P, and we have information about P conditional on D, so switching the order of the conditionality, this is the way we transform the things that we know about the test. How likely is it to tell us that there's a positive result when there should be a positive result? How likely it is to give us a positive result when there should not be, because the person actually isn't sick. And Bayes' law puts the information that we have together here to give us the information that we want. Okay. All right. So in the next lesson, we're going to put some numbers in here, and that's going to give us some concreteness to the example so far. Before I go there, let me just write the Bayes' law, and it's using my E's and F's here. Okay. So and let me write it using thicker pen here. All right. So if I have the if I want the probability of E conditional on F, I can get that from the probability of F conditional on E times the probability of E divided by, I'm going to apply the law of total probability to F here, the probability of F conditional on E divided by the probability of E plus the probability of F conditional on E complement times the probability of E complement. Okay, so that is one form. Just like with the law of total probability, we can have a finer partition of F rather than breaking F down into F intersect E and F intersect E complement. We could break it down into set of a broader set of conditioning events. Okay, so the other version, or let E1, E2, En partition as the probability of E conditional on F is the probability of F conditional. It's not a parenthesis there. Erase that, make it the conditioning part, what we want. F conditional on. What we want is E1 here. Probability of F conditional on E1 times the probability of E1. And then down here in the denominator, law of total probability again. So the probability of F conditional on E1 times the probability of E1 plus the probability of F conditional on E2 times the probability of E2 dot 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 all the way to the probability of F conditional on E to En times the probability of E. So just another form of Bayes' law, but rather than just thinking of the disease being present or not, the way we're doing in this example, or E being the case or not, we're thinking about what could be E1, it could be E2, we're just dividing up the sample space into a finer partition there. Okay. One last comment here. Everybody who uses Bayes' law always notices that when you write it down, you write the numerator, and then the first term in the denominator is always the numerator. Okay, so yeah, you'll notice that pattern when you do a few problems, and sometimes that can help you check yourself to make sure that you're doing it right. Okay, so next lesson we'll continue this positive test result disease example with some numbers, so you'll see how that works. And I'll see you then.